Okay, question 5 is all about moments, and we've got a 2 Newton weight placed 60 centimeters from the pivot point. So the weight is acting down from here, and that's causing around this pivot point here a clockwise moment. Okay, and that clockwise moment is trying to turn the ruler in a clockwise direction. Now the Newton meter is placed 10 centimeters from the pivot. Now in order to stop that clockwise rotation, the Newton meter is applying a force upwards. Now that causes an anti-clockwise moment, which is going to oppose the clockwise moment, trying to turn the ruler the other way. The first thing they asked is to state the equation that links moment, force, and perpendicular distance from the pivot. Well, moment is equal to force times perpendicular distance from the pivot. Now the next part, calculate the reading on the Newton meter. Ignore the weight of the ruler. Now, first thing we're going to look at is, well, the ruler is stationary there, so the whole system is in equilibrium. Now, if the system's in equilibrium, then we can say that the clockwise moment, or clockwise moments, but in this case there's only one that we need to talk about, the clockwise moment is equal to the anti-clockwise moment. Now, if we considered the weight of the ruler, but we've been asked not to, there'd actually be an extra moment here. So if you look up at the diagram, the weight of the ruler is also acting downwards, and that causes a second clockwise moment. But they've asked us to ignore that in this question, so they've made it a little easier. So we've only got to consider the moments due to the 2 Newton weights turning clockwise and due to the Newton meter turning anti-clockwise. So because we know that the moments are balanced, we can say that the clockwise force times the clockwise distance is equal to the anti-clockwise force times the anti-clockwise distance. And then we just substitute our numbers in. Well, our clockwise distance is 60 centimeters. Our clockwise force is 2 newtons. On the other side, our anti-clockwise force is what we're trying to find out, and that's at a distance of 10 centimeters from the pivot point. And once we've got to this point, we can just solve for F. The F, anti-clockwise F, is going to be equal to 2 times 60, 120, divided by 10. That gives us a 12 Newton force. So the key point here was that we realized that the sum of the anti-clockwise moments must equal the sum of the clockwise moments. Now we're then going to replace the metal ruler with an iron bar. Now the iron bar is the same 1 meters across, but this time it's a weight of 10 newtons. Now last time we could ignore the weight of the metal ruler because it was so small that we didn't have to consider it. Now we do. Now the Newton meter and the 2 Newton weights stay in their original positions, so we're not altering the distances at all. But you've got to explain, you don't have to do the maths here, but you can explain how this change affects the reading on the Newton meter. Well, hopefully you'll realize straight away that if you put a heavy iron bar instead of a meter ruler, that's going to increase the weight, and therefore it's going to increase the clockwise moment. So therefore, the Newton meter is going to have to produce a bigger anti-clockwise, so a bigger force. Okay, so what we want to say here is the force on the Newton meter will increase. And then we need to give 2 good reasons for why we say it's going to increase. And what we're going to say then is the weight of the ruler, or the bar, sorry, produces an additional clockwise moment. So we already had 1 clockwise moment. That was due to the 2 Newton weight. Now we've got a second moment too. So we go back to our diagram. We had the 2 Newton weight producing a clockwise moment, and now we've got the mass of the bar producing a second clockwise moment. Now because we've got 2 clockwise moments, we're going to need an even bigger anti-clockwise moment in order to balance them. Okay, so the force on the Newton meter is going to increase, and that's because the weight of the bar produces an additional clockwise moment, And we then need a bigger anti-clockwise moment to balance the clockwise. And if I don't balance it, then I don't have equilibrium. If I don't have equilibrium, then that bar or that ruler is going to turn one way or the other. In this case, if I can't balance the force with a Newton meter, it's going to turn clockwise around the pivot bar.